Hello. Today I'm gonna be doing a calculus again. I did do one with my voice not that long ago, but now I'm doing another one. I'm not sure which one I did my video on. I think it was the Taylor series, which was kind of back later now. But I'm doing another one, and it's gonna be an extra long one this time. So I don't know how long it's gonna be. I'm trying to do. And this is something I called a math marathon, or MM, which is something that I just made up, but it's almost like a marathon, it's long distance. It's very long. It's very tough. Math is tough too, definitely. So I'm going to be doing a long amount of math with multiple lessons. This isn't really to explain anything. This is just me learning it at my own pace and my own learning. If you need a tutorial for anything, I best would recommend going to another channel that has a specific video for this. This video is just going to be me doing multiple lessons. And I don't know how I explain them, but it may be easier to an adult who has knowledge to be able to explain the information and equations well, to basic to advanced. Okay. Yesterday I was computing limits number 2. Well, I think it was on, not yesterday, but the day before. But I took a 1-day break for this since I'm going to be doing it extra long. And today I'm going to be doing that. So this may be split up into 2 parts, and still in one video, but not all in one time. Because I don't think I can do it super duper long in one time. This video may take a little longer too. I'll start now. So we're going to start on the squeeze theorem, which is very interesting. It's kind of like here, as we started, you'll kind of see why. You've seen this a lot. I think everyone sees this very often, how this works. So it involves a lot of math. We can see here, here's the starter paragraph, the squeeze theorem. Miranda just built a new pig pen, and she needs help corralling these ornery creatures. We can make the fencing into a pen as wide as narrow as we want. The easiest way is to make sure all the pigs end up in the curl to make sure the gap is as narrow as possible. This gets us thinking about a limit problem we saw us heading out to the farm. As we can see here, look at this. Pigs bounce really far. And look at this. Do you see that? So, as the pig bounces, as it gets closer to the enclosed area, it goes more faster, a rapid way, right? And then it goes the opposite too, where it's more expanded and bouncing back and forth. It's kind of the squeeze theorem where once something is in a very tight space that isn't very big and may meet its size, and it's at a very fast pace. I don't know how fast it needs to be, but it involves a lot of math, but it affects how much it bounces. And the tire bounces very fast. And then it could also get so bounced that it didn't really bounce. But there is a point where if it meets its mass, that it won't bounce anymore. But still everything else has the equation that the tighter it gets, the more the pigs will bounce, or whatever object. Okay. In the graph below, if we follow a red point along the green graph of y equals a function of x, we trace out a path very similar to the pig's erratic run. The blue graphs are given by negative g bottom x equals h top, x equals b, which if it was just b, it would be x is less than 1, or x plus b minus 1, which is when x is greater or equal to 1, where b is a constant in this equation. Just like the pig trapped by the fencing, the graph of function x is trapped, as we can see by this equation. Look at this, as we get closer, this would be considered the pig. As it gets farther, it bounces less. As it gets more enclosed, based on how far it was away from this, it eventually gets way too tight and bounces at a rapid rate. Everything will stop eventually once it reaches its point, but it's interesting to see this, how this works. And it also depends on how immediate or how much force is going through it too. If there's no force on it or no strong bounce, it may come in very slowly, not even bounce at all. But if we had an equation where it was bouncing at a constant force and rate, this is something it would look like. It seems like it always meets a certain point though, just meeting all the ends. As we can see, it bounces rapidly at this, but even if we make it wider, it still bounces at a very rapid rate in this certain area, as it's tighter than the surrounding area. Even if we make it super small, it still bounces at a very rapid rate, as we can see here. So it looks generally equal, even if the size is much bigger or much smaller. Okay. What is the only choice for b when we are guaranteed the limit of x to 0, function of x equals 0? Here, let me think of this. What is the only choice for b? It's a little confusing when I look at any other info I have. So it would be 1 digit. So negative g bottom equals h top. I'm trying to think based on this equation. This equation probably gives the answer. This one up here, the top one, it probably will most likely show the answer. Maybe 2, possibly. 0. I'm a little confused. I was looking at this equation. How would relate to this? And now it seems like it makes more sense. Let me see the explanation. It's easy to see that the limit of x to 0, h top, x equals b by definition. So the graph of function x is stuck between negative b and b, which I guess we could see here. If we squeeze the throat shut by taking b equals 0, the function f(x) has to approach 0 as x is a 0. Oh yeah, that makes sense. See here? Like it doesn't even look like it's moving anymore. Can you see that? You can see by this. It just doesn't even look like it's moving. Because like the line is like smaller than the item's mass too. Just like the pig and the coral, function x has no choice but to go to the origin of b equals 0. Okay. Yeah, we could see that here if we do it super tight. The pig mass is almost equal to the thing, it can barely even fit. So it has the result of 0. See, the pig looks like it's not even moving. We're on our way to understand one of the most important limit tools, the squeeze theorem. Like many other theorems in basic calculus, it is easily to visualize, hard to put into words, and even trickier to use. So it's tricky to use and easy to visualize. So yeah, the math is very hard, but this looks pretty basic. Like, oh, it just at the rate, it just gets tighter and tighter and goes at a more rapid rate. But the math is definitely very hard, and saying it is going to be hard, so wish me good luck. This lesson focuses on building our squeeze theorem notation through geometric examples. The centerpiece of this lesson is proof that the limit of x 0 plus sin x over x equals 1, which we can find trigonometry derivatives. Basic trigonometry knowledge will be helpful towards the end. The pig example shows us as long as there are bonding functions, or gx is less or equal to hx, trapping y equals fx above and below. So it would be less or meeting points, which would mean trapping, or 0. Or it's less where it's open and the force is bouncing at a rapid rate. Trapping y equals function x above and below. And we could also see this equation, which has requirements. The limit of x to a, function of x equals L if the limit of x to a to gx equals the limit of x to a hx equals L. So that means basically every single one, fx, gx, and hx have to equal L. And if else, this won't really work. Because this only works limit of function of x if limit of gx is equal to limit of hx, which is equal to L. So they all basically have to equal L. In this graph, hx equals 2 minus b cosine pi x in green, and gx equals 1 minus x minus c to the second power. In red are designed to contain function x colored in blue. So the first one is in green, the second one is in red, and the blue is the function of x, which is the one that gets tighter. So the lower bond, the upper bond, and then the x function of x. Let me see how this would work. You see how? Look at the other ones, equations. Look at how they affect this. Do you see this? And then if they meet, look at this. It's very interesting. It's weird how this affects it. Can you see like how it almost like moves the graph like it's like a mountain? It almost looks like a mountain. And then this is almost like a line on top of it. It almost seems like mountains that generally like push it forward or backward. Let's see if this wasn't here. And this affects it too. You can see a little bit. The graph moves a little bit. And then they both generally affect it. For what common values of b and c do the two functions share a common limit L equals 1 at x equals 2? So if we go to x equals 2, what values of b and c to the function? The limit is 1. Well, it almost seems like they meet. Do you see this? Look at this, how they like meet. That's what I was showing. So it probably would be c equals 2, b equals 1. Look at this. They like are like perfect. Yeah. If we dial b equals 1 and c equals 2, the green and red curves squeeze together at x equals 2 and limit x to 2 function x equals 1 for CERN. Like, this looks like the best, only meeting 1. I wonder if this would work. Not really, because it doesn't affect the main part of the graph. This seems like the best choice because it hits the most rapid part of the graph. Here's the gist of what we found regardless of what y equals function x looks like. If 1 gx is less or equal to a function of x, which is less or equal to hx, close to x equals a, and 2, limit x to a, gx, equals limit x to a, hx, equals L. So, if they have a good meeting point, look at it equals L. Look at this. It's really interesting how the math works. And then limit of x to a function of x equals L too. As we can see, look at every single graph. They meet everything perfectly right here. Exactly. It looks very perfect, doesn't it? Every graph looks. Then limit of x function x equals L2. The curves y equals gx and hx squeeze y equals fx into L as x to a. See, we can see both gx and hx squeeze y fx into L as x to a. So they almost like force it into, which I mean it still works, it still makes it L. The squeeze theorem can be challenging to use in practice. The hard part is finding good bonding functions. When the limit involves sine or cosine, a good strategy is to use -1 is less or equal to sin z, cosine z, or is less or equal to 1. For any real z to build the bonding functions. So it has to be between -1 and 1. How it seems like. Consider this limit. The limit of x to 0. So 5 plus 2x to the second power sin is 1 over x to the 7th power. Use the squeeze theorem to compute the limit. So what would be the limit for this? So x is 0. That's what its limit is, at least. So it's guaranteed to be less. Sine also has to be. Wonder if there's any hints. No. So it's gotta be a 1-digit answer, most likely. It seems like most accurate. So, we can always consider the x limit is 0. So, would it be 0? Because this squeezes as x to a. I wonder if that would relate. 5. There's a 5 right there. Let me see, because I'm a little confused. It's always good to learn about it. Exclamation. First direct substitution won't work here. Try plugging in x equals 0 and you end up dividing by 0. So the function is only defined as x does not equal 0, in which case -1 is less or equal to sin. 1 over x7 is less or equal to 1. Moreover, since x to 2 is greater or equal to 0 for all x, we have -1 is less or equal to sin, as we can see, the equation we got before. And then instead, let me see what they do. So they basically multiply everything, it seems like. So they do 2x to the second, or 2x to the second power times -1 is less or equal to 2x to the second power times sin 1 over x to the 7th is less or equal to 2 times x to the second power times 1. So this does come in handy, the 2x to the second power. That's what we basically receive. We take the sin 1 to x7, and then instead we just use the 2x to the second. And then that would most likely eliminate all the -1s and 1s, as we can see here, and then we add the 2 after that. I mean, not the 2, the 5 after that. And then we receive 5 -2x to the second power is less or equal to 5 plus 2x to the second power sin 1 over x7 is less or equal to 5 plus 2x to the second power. So it makes somewhat sense, and then we can define that also as gx equals 5 -2x to the second, and the rest is the same. hx equals 5 plus 2x to the second power, and function x equals 5 plus 2x sin 1 over x to the 7th. It's interesting because it also goes with the formula of gx is less or equal to function x, and the function x is less than or equal to hx. And that kind of goes with the equation. So that's kind of like a good formula to remember when you're trying to solve it. So it's good to start with the sin 1 over x to the 7th, and then adding on and using basic multiplication, division, and /subtraction to do it. Then the limit of x to 0, gx equals the limit of x to 0, fx equals the limit of hx, x to 0 equals 5. Because it just seems very realistic, as we can see in the equation. If x is equal to 0, or is less than 0, that's what it would be. That makes a lot more sense now. The squeeze theorem is particularly suited to handle Wily equations of sine and cosine. Now consider this limit. The limit of x is infinite. 2 plus cosine times sin x over x. Use the strategy of the last problem to compute the limit. So the limit is infinite, so x could be anything. We could always consider x as 1. So, let me go up here. Cosine and sin are always between. Let me see. So either of them are always between -1 and 1. So we would it be arguably 2 if others eliminate each other? If they're between 1 and -1? Will they technically eliminate each other? Here, I might try that. It just seems very realistic from the last one. 0? That's a little weird. I thought it would be 2 from the last equation, how it was basically the same. And the limit of s, sin, and cosine, I thought they would eliminate each other and the x would eliminate each other too. And then we were just received 2. Let's just see what I did wrong. So first we need to recall that -1 is less than or equal to cosine. Sin x is less than or equal to 1. So that's why I was thinking they will eliminate. But I guess they really eliminate. For all real x, even though the expression looks complicated, -1x is less than cosine sin x is less than or equal to 1. And then we do, I guess, what we did last time. We add the 2, and then we add the x. And then we do 2 plus -1 is less than or equal to 2 plus cosine sin is less than or equal to 2 plus 1. And then we put x. So since we're looking at x to infinite, x is certainly positive and the last inequality holds. From the squeeze theorem we have the limit of x is infinite, 1 over x is equal to the limit of x equals infinite, 3 over x is equal to the limit of x to infinite. So I guess it would only work, it would work out if it was 0, because they would just eliminate, and then you would eventually get 0. That makes a lot more sense. So I guess it's not more of a cosine, sine eliminate each other. That wouldn't that make that sense? It relates to another equation. The first equation where we just add everything. Here, I might try that. If I get another question, I'll make sure to remember that. We can't use -1 is less than or equal to sin z cosine x is less than or equal to 1 to construct bonding functions in every situation. Take a limit of x to 0 plus sin over x divided by x equals 1, the centerpiece of this lesson. The strategy of the last two problems gives us bonding functions. So as we can see here, this is gx and this is hx. -1 over x is less than or equal to sin x over x is less than or equal to 1 over x, which is basically the same. Well, not really the same, but it has the same like it's just instead of -1, it's -1 over x. Instead of 1, it's 1 over x. That does affect it a lot more than you think. But we can now use the squeeze theorem since the gx and hx diverge to plus or minus, negative or positive, infinite as x goes to 0, plus. We can still use the squeeze theorem, but we'll have to be a little more creative. To find the limit of x to 0, sin x divided by x, we're going to rely on our knowledge of trigonometry. We start by inscribing a right triangle with interior angle 0 inside a circle of radius 1, as shown in the figure below. So, what is the area of the triangle? So, the circle has radius 1. What is the area? So, so it has interior angle 0. It's at a circle radius of 1. I believe it would be 1/2 tangent, wouldn't it? Most likely be 1/2 sin and cosine. Yeah, I was kind of understanding the half point. It made sense based on an equation. I knew it was half. Must have forgot my trigonometry. Since the hypotenuse of the triangle is 1, the side opposite 0 has length sin x, and the side angle has cosine 0. Since the area of any triangle is 1/2 the base times the height, we have A equals 1/2 cosine 0 sin x 0. Yeah, that makes a little more sense. So, we're going to have to do a lot of trigonometry to solve this equation. Graphing, I guess, is too hard. Or maybe might not even work. Using the same circle, we construct a larger right triangle with interior angle 0. What is the area of this larger triangle? So the last one we saw was sine and cosine. Would it arguably be the same equation? Because I was thinking about sine to the second power, but triangles don't really work like that. Of course, I switched them up. I guess better like next time to me. Since tang 0 is the ratio of the opposite side length of the agent, which is 1, it follows... Oh, it was the opposite. Yeah, that makes sense. Which is 1, it follows that the height of the triangle is tang 0. Since the base has length 1, the area of the triangle is A equals 1/2 tang 0. The area of a sector of the unit circle is 1/2 0 when 0 is measured in radians. This and the areas of the triangles of the last two problems are summarized here. So we can see this. So a sector, a inner, and a outer. So these can be used as the graph. So they're basically used as the graphing points, it seems like. So a sector, a outer, a inner. Use the diagram to find a coupon inequality for 0. So now they're all placed on top of each other. They do all meet 1 point, you can see here. So we saw that the bigger triangle was tang, so that would most likely be on the top. So it may be like this, I believe. Yeah, since this looks like the right equation to me. Yeah, it is. It just looks like the size and everything. It looks pretty obvious. Sine and cosine is the red. Then the normal 0 is the green. And then the tang is the blue. It goes in order also, like the G, X, and then the fx and then the hx. As we can, here, let me take a picture of this to remind me. The red triangle fits inside the green sector and both fit inside the blue triangle. Therefore, a red triangle is less than or equal to a green sector is less than or equal to a blue triangle. Or 1 over 2 sin cosine is less than or equal to 1 over 2 0 is less than or equal to 1 over 2 tangent. Multiplying through by 2 gives us the desired inequality. Sine cosine is less than or equal to 0 is less than or equal to tangent, which is almost like the equation for the graphic. It's pretty much the same. That's interesting. In the last problem, we found out that sine cosine is less or equal to 0 is less than or equal to tangent. For, as we can see in this one, for small positive angle 0. Starting with sine cosine is less than 0 and dividing both sides by 0 cosine 0, we find, as we can see is in this equation, instead it would be sine 0 over 0. If we eliminate others, would just be sine 0 over 0 is less than or equal to 1 over cosine 0. We can see by the elimination, these cosines eliminate, and then these zeros eliminate. Since tangent 0 is equal to sine 0, divide by cosine 0, we also have 0 is less than tangent 0 equals sin over cosine is, or could be, cosine 0 is less than or equal to sine 0 over 0. That doesn't seem that much sense, as we can see by this equation. It almost seems like a turnaround, but I guess they can't technically be equal. After we multiply both sides by cosine 0 and divide both sides by 0, all together we have cosine 0 is less than or equal to sine 0 over 0 is less than or equal to 1 over cosine 0. So we get a more organized formation, as we can see in this way. It kind of relates back to the normal trigonometry solving for less shapes. This kind of relates. It reminds me of sine and cosine, how sine and cosine could be primes of each other. Okay. Calculate the x is to 0 plus sine x over x. So x would be 0. And that arguably just be 0. 1. Replacing 0 with a variable. Oh, we just replace and eliminate, and then we receive the same answer. Because we could see by, where is that one up here? As the elimination, as we eliminated these two zeros right here, the one on the top and one on the bottom, we just put 1 on the top. And then we could use the squeeze theorem too. That's basically it. Looking ahead to calculate the derivative of sine x, we need to know the limit of h to 0, sine x times x plus h minus sine over x divided by h. We can use our squeeze theorem results to find the different quotient limit exactly. The squeeze theorem shows us that the limit of h, 0 plus sine h divided by h equals 1. Since sine h is an odd function, it also follows that the limit of h to 0, sine over h equals limit h is 0 negative sine h over h equals the limit of h to 0 sine h over h or equals 1. As we eliminate, it would just equal 1. Let me see. Just looking at how it would work. Yeah, we can also see h0 plus will also equal h0 minus, which, and then also to h0, which, if h is 0, it would just equal 1, if they eliminate. As a coincidence, or as a consequence, we can also show that the limit of h to 0, 1 minus cosine h over h, equals the limit of h to 0, 1 minus cosine times h over h, times, if we include 1 plus cosine h over 1 plus cosine h, since they can technically be positives, which that end result will equal the limit of h equals 0. We can set up negative cosine. We can also do sine and eliminate the ones, and then on the top, and then we would get sine h over h times sine h over 1 plus cosine h, which altogether, by eliminating everything, would equal 0 once again, which is really weird. Let's start with sine x times x plus h. In this difference quotient above, by the sum formula for sine times x plus h equals sine x cosine h plus sine h cosine x. That makes sense. Therefore, as we can see here, sine times x plus h minus sine x over h would equal sine x times cosine x plus sine h times cosine x minus sine x. As we can see here, we subtract. That's actually really interesting. So they are basically the same thing, because we can minus sine x and receive the same thing. Oh, look at this. We would receive, basically, instead, if we did, we would just do negative sine x times 1 minus cosine h over h plus cosine x sine h over h. That's interesting. I need to take a picture of that. So in the limit where h to 0, we have the limit of h to 0, sine x plus h, negative sine x over h equals cosine x. We computed a very important rate of change here using the squeeze theorem. We'll have to wait until later to fully appreciate how important this formula actually is. In summary, the squeeze theorem is an important limit theorem used in higher mathematics. In basic calculus, the squeeze theorem is typically used to control Weyl equations of sine and cosine. Its most important application for us is proving that the limit of x to 0 plus sine times x over x would equal 1, without which we cannot calculate the continuous rates of change of the trigonometric functions. And then we finish that lesson. That was interesting. Just skip this. And then we can go to the IVT application, Root Finder. Let's see what that is. We'll start this. I'm doing more lessons too. So if you like to skip forward or stop watching or something, you may. IVT application, Root Finder. Explore the intermediate value theorem and its uses. Let's try, I guess. IVT application, Root Finder. True or false? The polynomial px equals x to the fifth plus ax to the second plus bx plus c always has at least one real root, no matter what we choose for a, b, or c. Arguably no, because usually they could be repeating. Sure. Why is that? Surprisingly, the polynomial p times x always has at least one real root. Here's one way to see why this is true. Because p times x has an odd degree, I guess keyword is the odd degree, I guess affects it. The limit of x is negative or positive infinite. Px equals negative or positive infinite. So they equal any number between negative or positive infinite, which is everything. We go far enough to the right of the origin, p times x is eventually positive. If we go too far enough to the left, it is eventually negative. Since px is continuous, it has to go through 0 at some point, and therefore has at least one real root. This argument is based on the intermediate theorem, IVT, which we review next. So it always will meet 0 no matter what, so it always has at least one real root. The IVT says that if the function of x is continuous and that the graph passes through y equals a and y equals c, where a is less than c, then it also has to pass through y equals b for Sorry for the pause recording, there was a notification that messed it up. Okay, as I was saying, where A is less than B is less than C at least once. So B always has to meet somewhere in between A and C. It's just not possible for it to not. Y equals function x crosses y equals b at x equals a. No matter how hard we try, we can't skip over y equals b without breaking the curve. So we do always have to meet b. It's just not possible not to, because it's somewhere between a and c. At least in how far they are apart, no matter what, it has to meet b in some way or another. It would be not realistic if it wouldn't. Or if it did not meet, that would not be very realistic, and that probably wouldn't work in anything. Okay. Our goal... We'll touch on one very simple and important application of the IVT, root finding. Our goal is to use the IVT to write code implementing the bisection method for finding roots of a function of x. We'll assume that the function of x is continuous and has at least a unique real root. Some experience with algorithms and computer programming would be helpful here, but not necessary. Well, I don't have any computer programming experience. I do have a little bit with coding, not very much though. I don't know if that helped. Let's develop an IVT-based root finding algorithm by focusing on a specific continuous function. The function of x equals cosine times pi over 2x minus x. Using only the IVT, select the interval containing the unique solution of function of x equals 0. So, if it was pi over 2, function of x would equal 0. Where would it have to meet? I believe it would be negative 2 over 1. That seems the most realistic. 0, 1? Yeah, you think I guess that would work for the equation. I thought it would be negative, I guess. Let's look at the endpoints of 0 to 1. The function of 0 equals cosine pi over 2 times 0, negative 0, equals 1 is more than 0. And then the function of 1 equals cosine pi over 2 times 1, negative 1, equals negative 1 is less than 0. Of the options presented, this is the only interval where f has different signs at the endpoints. Since the graph function x goes from positive to negative 0, 1, the IVT guarantees that the unique root is in this interval. So this equation where it goes from positive to negative, you have to have a unique root, or possibly b. From the last problem, we know that the root of function of x equals cosine pi over 2x minus x is in the interval 0 to 1. Now let's bisect this interval. That is divided into 2 equal side subintervals. So 0, 1 equals 0, 1 over 2 union 1 over 2, 1, or 1. The root has to be in one of these smaller subintervals. Which one contains the root? I believe it would be 0, 1 over 2. But it seems just... Yeah, it would be most likely 0, I think. 1... You see what? We already know that the function of 0 is less, is more than 0, and the function of 1 is less than 0. Since we find the function of 1 over 2 equals the square root of 2 over 2 minus 1 over 2 is more than 0, the IVD guarantees that the root is located in 1 over 2, 1. I guess that would make sense since 1 is the constantly changing point. Okay. The root of function of x equals cosine pi over 2x minus x exists somewhere in the interval 1 over x or 1. Let's bisect this interval. 1 over 2, 1 equals 1 over 2, 3, 4, union 3, 4, 1. So we're just bisecting it into smaller equations, or equations that would work out. This root has to be in one of the smaller 2 subintervals. Which one contains a root? You may find cosine 3 pi over 8 equals, or is almost equals 0.3 useful. So, would that mean that I don't want to get this wrong like last time. So, it most likely would have to meet on the axis, right? Arguably, it would have to meet here. So wouldn't it be 1, 2, 3, 4? Yes. Okay. Phew. It seems the more sense because if we go back here, look in this graph how it's almost like flat. It has to be somewhere right here in the middle. That kind of meets the point. And then let's see the explanation. From the hint, a function of 3 over 4 equals cosine 3 pi over 8 minus 3 over 4 is somewhat equal to 0.3 minus 0.75 is less than 0. It also is almost, we can see it's somewhat like equal to, because pi is really close to 3.14, which is very close to 3, and they almost have a somewhat equal equation. From the last problem, we know the function of 1 over 2 is more than 0, so the root has to be 1 over 2, 3 over 4 by the IVT. It has to meet somewhere on the x-axis. The midpoint on the interval is 1 over 2 plus 3 over 4 divided by 2 equals 5 over 8, or 0.63-ish. The actual root is approximately 0.6, so the midpoint of the interval does a fairly good job approximating the true value. Here's the pattern that's shaping up. Suppose a is less than b f function of x is continuous, and the function of a and function of b have opposite signs. By the IVT, a, b contains a root of function x. Negative. Let's assume it's the only root. Either a plus b over 2 is the root, or the root is in a plus b over 2, or a plus b over 2b. And the IVT can show us which one. This becomes the new interval in the next part of the loop. By repeating as many times as we like, we can isolate the root in the interval of length b minus 1 divided by 2 to the n. We take the midpoint of the last interval in the process as an approximation for the root. Since the limit of n is infinite, times b minus a divided by 2n equals 0. The more times we repeat, the better approximation. So we can repeat the equation to get a better answer. Here we're going to have some coding. Here's an implementation of our bisection algorithm in Python. Play around with nmax and TOL below. Here TOL is short for the amount of error that you're willing to tolerate, and nmax limits the number of times the loop runs. So let's run it. So look at this. Let's just see. Import math. Definite sign AB compares the sign of two numbers. Sign is less than 0 if A and B have same sign. Return A times B. Def bisection. XL, XR, TOL. N equals 1. Let me look at this. Prevent infinite loop. Error equals ABX times XL minus XR divided by 2. And then we can run the loop. And see, as we get closer and closer, we just repeat the same process of finding the IVT as we did up here. See right here, we estimate, and we can repeat that. Go from, as we see below, see? We get closer and closer to what we were trying to go here. Right here. So, let me see how we repeat it. So, yeah, look at how much it runs. It gets more and more accurate. See, look how close it is. All the little numbers, we can just repeat the process. Enter your best estimate for the root of function of x equals cosine pi over 2x negative x. So, where are we estimating? What were we estimating? So, on the best estimate for the root. We can see here it's getting closer to 0. Wonder if we can do that far. 946. Okay. Yeah, look at how close it is in the last two numbers. It almost looks like it's repeating, even though it's not. Approximating estimates the root to be about 0.54612, which is a little more accurate than mine. The algorithm matches the approximation to 4 decimal places with the default settings n max equals 50 and TOL equals 0.0001. So the max is 50 outputs. And then TOL is 0.001. TOL is the amount of error that you're willing to tolerate. So that's how much, 0.0001. So that's how much it can be off or spaced. The function of x equals x to the third power plus 2x minus 10 has a unique real root. Let's run this. Sin x error, invalid sin x. Look at this, it's an error. The function, so this equation has a unique real root. Let's repeat it again. See, it has an error. Line 31 XL equals nothing. So XL, look at TOL equals 0.001, XL, XR, having errors. Approximate using the bisection algorithm provided. You'll have to enter initial values from the left and right endpoints, X1 and XR, or XL and XR at the bottom of the code. So we have to enter code. I'd rather not delete those, just in case. So, let me start with XL. Fine. So, let's do 6 and 2. It almost seems like 2. Look at this. Look how close it is to 2. I'm going to say 2. 1.85. I guess I didn't do it enough. Mathematica approximates the real root is 1.84742. We can match this approximation fairly close to tolerance as 0.001 and n max equals 50 together with x1. Let me see if I could receive that. Oh yeah, look at this. Yeah, look at 2, 3. So, and then we can see the question. The following that the root is somewhere between 1 and 2. Yeah, and this looks, yeah. I just didn't estimate enough. In this lesson, we saw a surprising application of the IVT, root finding. We implemented the bisection method in Python and used it to approximate solutions of function of x equals 0 for continuous functions with unique roots. As we can see here. It's honestly really confusing. Look at all this code. How we can repeat it. While software like Mathematica maybe use Softict, root finding methods, the bisection method is typically the first method encountered because of its relative simplicity. Learning it is the first step towards understanding more powerful methods for solving math problems on computer. Yeah, big math questions like these are very hard on computer. A lot harder than you think, especially like solving it. Their code is very hard. So a lot of the questions are usually estimates. Let's do precise definitions of limits. Precise definitions of limits. To wrap up our coverage of limits, we're going to revisit the very definition of the limit. We relied a lot on our intuition when dealing with limits. We know that the limit of x to a function of x equals L means that the function of x can be arbitrarily close to L when x is made sufficiently close to a, when this isn't enough to satisfy a professional mathematician. In this lesson, we'll cover the basic of the precise E or to S definition, focusing on what it means geometrically. I swear, I don't know what this. I know what this is, but I don't know what it's called. I wonder if I'll save that for later, because I still don't know what it's called. The material here won't appear anywhere else in the course. When we complete the optional lesson, we'll get a glimpse of how professionals do math. As we move forward, keep in mind that a minus b is a standard way of measuring the distance between two real numbers. Let's play a game to set the stage for ES definition. This is a two-player game, but you can also play as your own opponent. The game starts in the next problem. Here it goes. One player is E, the other player is S. E player chooses a value for E. S player tries to box the graph so that no part of y equals function x between the green lines representing A lies above or below the blue lines representing E. So, representing a reasonable number of times for each function x. S player only wins the function of x game if the graph can be boxed no matter what the E player chooses. The choice of S does not have to be the same for every function f equals x. So we have to box in the equation, it seems like. So try to box the graph some more. So no between the green lines representing lies above or below the blue lines representing E. So it can't go below. So we have to go between the green line. And we only have a few choices. So let's start with number 1. Only wins if the graph can be boxed no matter what the E player chooses. So this one's so we can, in this plot, we can control over two positive real numbers, S and E. We can also toggle between several function options with slider label function X and the number L equals 0 at the point limit A. So this doesn't work, as we can see here. Look at this. No matter what we do. Go to 2. Try to box that in. Nope. This wouldn't work, arguably, right? Because it goes above or below. Wouldn't this arguably be 0? if the graph can be boxed no matter what the player E chooses. Any player tries to box the graph so that no part of y equals function x between the green lines represents I lies above or below the blue lines. Wouldn't that be impossible though if this meets right here? Doesn't it still technically meet? Because I feel a little confused. So, because this feels like it could possibly, if I guess no, this reaches 0, it wouldn't. No matter what we do. Because they're either outside or inside. And they can't be outside. Sorry I have all these websites open. I would arguably say 0. Because it just doesn't seem like anything works. Like, if this can reach 0, literally nothing. These are the only things I thought had a chance. But they can't lie above or below the blue lines representing. I would say 0. 3? That doesn't seem right. The two functions that are not winnable are option 3 and 5. There is a jump in the graph of x equals 0. Because of this jump, it is possible to choose E small enough so that no choice of s can completely box the curve. Option 5 oscillates rapidly and needs x equals 0. Because of this rapid oscillation, it makes it impossible to box the curve with any choice of s if E is small enough. How do these other ones work? Let me look at the next one. To win the game in the last problem, the graph of y equals function x has a box between y equals L plus E and L minus E when x is between A plus X. I'm just a little confused. Because it can't lie above or below the blue lines. The S player chooses or tries to box the graph so that no part of y equals function of x between the green lines representing S lies above or below the blue lines representing. I'm just a little confused how this would work. There you go. You may wonder why this game has to do with limits. Here's the meaning of the game. The function x is only winnable if and only if limit x to a function of x equals L. So what, do these all technically equal L? Except 3? Yeah, that does. Oh, I guess. See, look at they all meet here, no matter what they do. These don't meet, just look at this, and this is just way too rapid. It's a mess. Here's the meaning of the game. The choice E is more than 0 is arbitrary in boxing the graph y equals function of x between y equals L plus E and y minus E when x is between A plus X and A minus X. Means that we can always choose x values close to A where function of x is guaranteed to be close to X. So that makes sense now. Look at these. They all meet in some way. See, this one, and this one. That makes a lot more sense. I can feel dumb now. Here's the e to s definition of the limit. The limit of x to a function of x equals L, and if for any e is more than 0, there is an s that is more than 0, such as a function of x minus L is less than e whenever x, or the absolute value of x minus a, is less than s. So we can see here L and A. We know that the limit of x to 3 2x equals 6 by direct substitution, but that doesn't tell us a relationship between e and s. Take a look at graph of y equals 2x below. The blue slider allows us to choose the value of e, and s changes in response to e according to the pattern. Oh, so we need a box. Yeah, that actually works. According to the pattern. What is the pattern? S equals e over 5. So I see. So wouldn't it be this? E divided by 2? Yeah. Let me see how that works. Here's the definition of the limit again for reference. The limit of x to a function of x equals L, and only if for any e is less than 0, there's a s that is, e that is more than 0, there's a s that is more than 0. Such that the function of x minus L is more than e whenever x minus a is more than s. So there always will be a s that's more than e. Choose a few arbitrary e values like 0.25, 0.2, 0.15, etc. These correspond to 0.125, 0.1, 0.075, etc. So we notice a pattern along the numbers. Y equals e divided by 2. Why is that s equals e divided by 2? If x, the absolute value of x minus 3, is less than x equals e divided by 2, then we see that 2 times the absolute value of x minus 3 is less than e. So that's basically just adding a 2 and multiply that equation. After we multiply both sides by 2, pulling the 2 inside the absolute value, we find x minus 3 is less than s. It goes to 2x minus x is less than e, so everything's double. For any given e's, it shows that if we choose s equals e over 2, then x minus 3 is less than s, is less than 2 times x minus x is less than e. So the limit of x to 3, 2x equals 6. That states it well. That makes a lot of sense. So e is practically double, it seems like. Everything is. The last problem gave us a hint about how to find s given e, at least in case of linear functions, function x equals mx plus b. Let's assume the graph is in a horizontal line. Then the limit of x to a, mx plus b equals L equals ma plus b. By direct substitution, but we want to know how e and s are related. Given e is more than 0, select the best possible choice for s. No, I got myself the answer. Wait, go back to I didn't look at anything, I promise. Okay. So I know it would be either maybe it would be this. I knew it would be absolute value. Here, let me see. We're given E is less than 0, and we want to find out S is less than 0. Such as we see is in this equation. Here's a strategy that can be very useful in these sort of arguments. Start with the absolute value of function at x minus L is less than E and reverse engineer S. So let's continue. Function of x minus L is less than E means the absolute value of mx plus b minus ma plus b is less than E. The b's cancels, and we are left with m times x minus a is less than E. After we pull out m out of the absolute value, dividing both sides by m, function of x minus L is less than E goes to m times x minus a is less than E, goes to x minus a time is less than E time over divided by the absolute value of m. Now we see why S can be S equals E over M. This explains by the pattern of S equals E2 in the last point where we looked at the limit E equals 3 to X equals 6. That makes a little sense, yes. Unfortunately, finding S isn't always straightforward. To make things even more complicated, two people may come up with two different S's for a given E. Let's think about the limit of x equals 2, x to the second power equals 4. So let's see that. Let's do option 1, as you can see. Option 2, option 3. I guess they're both like kind of different, see? We're given 3 options for S in terms of E. 1, which is the green one. S equals the square root of 4 plus E minus 2. Number 2. Let me take a picture of this. Actually, the video is fine. Number 2 is the S equals E divided by the 2, the square root of 4 plus E. They're kind of opposite. Or number 3, the giant one, is S equals E to the second power. No, I didn't look at the question. I keep doing that. I want a hint and it doesn't give it. I promise I look at it. I mean, they all, let me see. They all look like they work. See? They all meet. But I guess I'm probably off. You can't even pick that. Both 1 and 2 work. 1 and 2 are in related sizes. But they don't meet the same exact sizes. Only 1 works. X equals 2 minus. Oh yeah, that would work. Green, probably, only 1. Both 1 and 2? It just doesn't seem very accurate because it's a little smaller. Now let me see why. It turns out that both 1 and 2 work, even though they represent very different relationships with S and E. So is it possible that 2 people may disagree in the form of S, but they both could be correct? One quick way of seeing why 1 and 2 both work is playing the E-S game with the sliders. Of course, this doesn't amount to a proof, but it should be enough to convince you if you aren't interested in the details below. Formula 1 and 2 are quite complicated, and it takes creativity and experimentation to find them. Most importantly, it takes much patience. Instead of finding the S's from scratch, let's convince ourselves with proof that they work. If you aren't interested in the details of the proof, you can safely skip the rest. Keep in mind that proofs are what mathematicians live for. Okay, let's continue. Oh, okay. Suppose we choose s equals the square root of 4 plus e minus 2. Remember that we are trying to show that. As we can see, I'm going to read this. This is very long. You may read along, or you may pause the video. I will be reading quietly for this. Okay, so if you did pause this, and then we can see that it does seem challenging, but it's very hard, I guess, yeah. But you do end up receiving the answer you need, as you can see by all this math. I was reading it, and there's a lot of math, but a lot of repeating stuff happens too. So it looks a lot more scary too. Step 4, Formula 2. Formula 2 looks a lot more simpler. There's a shortcut here if you understand why Formula 1 works. It's possible to algebraically show that e over 2 square root of 4 plus 4 is less than square root of 4 plus e negative 2. When e is more than 0, therefore, the absolute value of x minus 2 is less than e over 2 over the square root of 4 plus e. Then it is true that x minus 2 is less than square root of 4 plus e minus 2. We know that already implies for x to the second power minus 4 is less than e. So they both relate back. And then that's basically it. We can take a shortcut we know in Formula 1. Formula 3, how it doesn't work. We'll show Formula 3 can't work by counterexample. Choose e equals 3, 4, and x equals 3, 2. Then the absolute value of x, negative 2, equals 1 over 2 is less than e. S equals 3 over 4 to the second power equals 9 over 16. But function of x, negative 4, equals 7, 4, which is more than e, which equals 3 over 4. that wouldn't work. Limits at infinity and infinity limits. So far, we've used E, S, and S to decide to precisely define finite limits. Infinite limits and limits at infinity both need rigorous definitions too. Intuitively, limit the x to a function of x equals infinite means that as x approaches a, the values fx get abruptly large. Consider these statements. 1. For every e is more than 0 that exists, s is more than 0 such that for all x, if 0 is less than x minus a is less than s, the function of x minus infinite is less than e. And then for every m is more than 0, there exists s is more than 0 such that for x, if 0 is less than x equals a is less than s, then f function of x is more than m. For every e is more than 0, there exists m more than 0 such that all x, if x is more than m, then function of x is less than e. So there's the function of x. There's. So we want to take our definition. Infinite. So this is m, which affects generally. Maybe m, one of the m's. Every m is greater than 0. There exists 0 is greater than 0. So that's for all x. Then or I would think 2. Let me say 2. Yeah, that makes the most sense. Because it just seems like this would exist if it's more than 0. If m is. And if we use the basic formula, which is used for everything, 0 is less than the absolute value of x minus a is less than s, and the function of x is more than m, as we can see by the high graph. And let's see the explanation. When working with limits, think of e and s as representing small positive numbers, and m as representing a large positive number. Since infinite is not a number, we can't make sense of function of x minus infinite, so the first option is incorrect. The second option says that x is sufficiently close to a, then function of x can be made abruptly large. This is the definition we want. The third option says that if we take x far enough away from the origin, function of x can be made abruptly small. Though not correct here, we may want this to keep this in mind for the next problem. Consider these 4 limits. The limit of x to 0, 1 over x equals infinite. The limit of x to 0 is 1 over x to the second equals 0. The limit of x to 0 is negative log x, or the x to 0 equals 1 over the square root of x. I think 1 is correct, at least, the number 1, due to Gabriel's horn, if that relates to it. I feel like that would relate to it, but I'm not sure. It's better give me a hint. No. Go back to her. I didn't see anything. I don't know. I think number 1 is correct, though. Because limit number 2 makes no sense. Number 3 makes no sense. Number 2, I'm not sure. It just doesn't seem accurate. I bet number 1's gonna be. Okay, good. Let me see why. I didn't look, I promise. Okay. Only one of the limits is true. I kind of was wrong, but I kind of was right. Because I said one of the limits, but I did the wrong limit. Why is the x to the second power true, but not the original x? Let me see why. Only one of the limits is true, which is the limit of x to 0 is 1 over x to the second equals infinite. And here's the proof. Let m be more than 0 be arbitrary. If 0 is less than x minus 0 is less than 1 over the square root of m, and then 0 is less than x to the second is less than 1 over m, the function of x equals 1 over x2 is more than m. Now here's why the next two limit. Wait, let me go back to this one. Now let's see why the next. Okay, that's it. Now let's see why the next two limits. The log equals infinite and limit 1 over square root of equals infinite. These limits are false for a subtitle reason. Remember, the limit of x to a function of x equals infinite means that for any m is more than 0, there exists a s at 0, such as if 0 is less than the absolute value of x minus a is less than s, then the function of x is more than m. In both cases, 0 equals 0 and 0 less than x minus a's absolute power is less than s means negative s is less than x, which is less than s. This set includes negative x values, which do not belong to the domains of negative log x and 1 over square root of x. It is certainly true that these functions approach infinite from the right side of 0 when they are defined. We write limit x plus 0 plus negative log equals infinite limit x to 0, 1 over square root of x equals infinite to indicate right-hand limits. So they're right-hand limits. No. Infinite. Finally, here's why the limit of x to 0, 1 over x equals infinite is false. This is what I want to know. The statement limit to x to infinite, 1 over x equals infinite, is false because the graph blows up to the right of 0 but shoots down to negative 0 to the left. That's why it's Gabriel's horn. We can see. Here, I'll look it up for you guys. Gabriel's horn. Look at this. As the graphing. Look at how it's negative and positive. It could technically go on forever. Like it could just go like up and down. And then it goes infinite forward. See, look at this. This kind of shows. It kind of goes on infinitely up and right. That makes so much sense now. I forgot about that. I was thinking of Gabriel's horn, but it goes up and down. It's false because the graph blows up to the right of 0, but shoots down 0 to the left of 0. We can prove this by contradiction, that is, we're going to assume it's true, and showing that this leads to something is impossible. Suppose the limit of x is 0, 1 over x equals infinite. Then for every m more than 0, there exists a s more than 0, such as 1 over x more than m. Then 0 is less than the absolute value of x is less than s. Choose a negative x satisfying 0. There. So choose a negative x satisfying 0. The equation. There are plenty of them. Then 1 over x is more than m is more than 0 is impossible since 1 over x is also negative. So m would be positive and negative at the same time. This impossibility means our original assumption limit to x equals 0, 1 over x equals infinite is wrong. That's really interesting. Now let's rigorously define limits at infinity. This plot below indicates... Wait, look at this. Before I say this, look at this, how it almost looks like Gabriel's horn. The red graph, right here. If you flip it around and put it together, you could imagine Gabriel's horn. That's how it relates. This plot below depicts limit to x to the infinite, e negative x plus 1 equals 1, and consider these three statements. For every e is more than 0, there exists m more such that for all x is more than m. Here, I'll keep all these equations for now. I won't read all of them. I'll read them until I get to the question, which is literally right below. Look at this, as e changes, m changes. As e increases in size, m goes backward. Or technically forward. That looks like it's going backward. With an example in mind, which of these three statements has the right definition of limit to x to the infinite function of x equals L? Let's see. Let me put this on. For every e is more than 0, there exists a m more than 0 such that for all x of x is more than m, the function of x minus L is less than e. For every m is more than 0, there exists a s more than 0 such that for all of x is 0 is less than x minus L is less than s. Function of s is more than m. For every e is more than 0, there exists a s such as for all function of x minus L. No function of x is more than L. Let me think of 2. 2 looks good. For every m is more than 0, there exists a s more than 0, such that for all x, if 0 is less than x minus L is less than s, then a function, I think 2. 1? Using the plot as a reference, we want a definition capturing this idea. Function of x can be abruptly close to L when x is taken sufficiently large. This means that we always find an m is more than 0, such as if x is more than 0, then function of x minus L is less than e, where e is more than 0 is arbitrary. So the first option is a correct one. Yeah, it wouldn't equal more than 0. In this lesson, we put the limit concept on solid ground. Precision is the main Mathematics is the only subject where we can be certain of a statement's truth. Not even the sciences can take that claim. This certainly depends on precise definitions and arguments like those we saw here. We do not ordinarily use e to s to calculate limits. The tricks we learned throughout the other lessons help us do that very nicely. Rather, e to s is used to prove that theorems, letting us know that those tricks are okay to use. We just scratched the surface of e to s, but more of advanced calculus courses start here. Instead of dividing into the machinery that makes limits work, we're going to move on to the most important application of limits, the derivatives. We finished that lesson. I'm going to pause my video for now. I'll crop this part back in, but I'm going to check out how much time I'm at. I'll be right back. Alright, sorry for the pause. I'll continue now. I had to do something. This is going to be my last lesson I'm doing for the marathon. And hopefully you enjoyed. I'm not sure how much I'll be at the end, but you'll see when I post this. Let's start with derivatives, because I don't want to get into too much of the derivatives. I'm mostly doing this marathon to finish the rest of the limit part, which was pretty big. Let's start with the derivatives, which is a completely new lesson. The derivative at a point. We decide that to define the speed at an instant, also called the continuous speed, we would measure distance traveled per time for smaller and smaller time intervals, like 1 second, 0.1 seconds, etc. Let's see what happens in the limit. Let's investigate more carefully. Suppose the function of t, time, gives our position along the positive x-axis as a function of time as we move from left to right. Let a be some point in time and t some point a little bit afterward. So a will be some point in time and t some point a little bit afterward. For example, maybe a is 1,000 seconds and t is 1,001 seconds. What quantity represents the distance traveled between time a and t? Let me just be time a minus time t. Or time t. Yeah. Since f tells us our position, we subtract the two positions to get the distance covered. We're told that t is more than a and we're moving left to right, so function t is a larger number of function a. So we want function t minus function a, not function a minus function t. To calculate continuous speed, we want to look at distance traveled divided by time interval. As the time intervals get smaller and smaller, think of a as a fixed time, and t as exchanging time a little after a. Which of these expressions captures the notion of continuous speed at time a? So, the limit of t is a function of t minus function of a divided. I would say this. We want distance traveled divided by time interval. From the last problem, function of t minus function of a is the distance traveled, and the time interval is t minus a. It's not just t. Remember from the last page, a and t could easily be 1,000 seconds and 1,001 seconds, respectively, in which case the time interval would be 1. In order for a time interval to get small, we would take a limit as t approaches a, not 0. In general, let f be a function. We're going to use x as an endpoint instead of t. So t, which was after, basically. After a. Correct? Yeah. Yes. So t is now going to be x. The derivative of f at the point a is defined to be the limit. So the derivative of f at the point a. Initially, the limit represents the change in output per change in input of the function at the point a. We also call this the rate of change of f at the point a. When this limit exists, we will denote it by function of the function prime of a. Okay. We can also see this notation, derivative of y divided by derivative of x, especially in the sciences. The second notation expresses the idea of change in y over changes in x, or the change in y divided by the change in x, taken to the limit as the change in x approaches 0. Sometimes the derivative is expressed as a limit as the change in x goes to 0. In this equivalent formulation, we don't take a limit as x approaches a, but as a quantity h, representing the change in input approaches 0. As we can see, by the limit of h is 0, function of a plus h minus the function of a divided by h. Suppose you throw a ball straight up just before time a1, and it reaches its maximum height at time a2. Let ft give the height of the time of the ball at time t. Which is greater, f prime a1 or f prime a2? So prime would be, so is the limit. Well, wouldn't it not be able to be determined? Theoretically? Oh. Let me see why. Function of a tells you the rate of change of f at time a. Right when you throw the ball, the function value, the height values are changing rapidly. As the ball reaches its max, the heights are not changing as rapidly. So the derivative at a1 is greater. In fact, the derivative at a2 is actually 0. So when it reaches its max, it's just 0. To say a little more carelessly, when f represents position, f prime represents speed. The ball speed is greater when you throw it when it's at its maximum. Or when you throw it than when it's at its maximum height. When it's at its maximum height, and then it's going to come down or actually lose force. And it's most likely at 0 at the specific time it's at its max height. Now let's go to the next question. Suppose a bug is moving counterclockwise around a circle at a uniform speed. Let the function of t give the bug's x-coordinate at time t. Suppose at time a1 the bug is at 0, 1, or 0, negative 1, and at time a2 the bug is at 1, 0. So they go from here to here. Okay, uniform. Function t give the bug's x-coordinate at time t. What is greater, f prime a1 or f prime a2? Wouldn't they be equal most likely? Still f prime 1? Why that? Compare how quickly the x-coordinates are changing when the bug is at 0, 1 versus at 1, 0. At the second point, the bug is traveling vertically, so its x-coordinate isn't changing at all. F prime gives the rate of change of a function's output. In this case, that means the rate of change of the x-coordinate of the bug. So f prime is greater at a1. So, let me read that again. Oh, it's the x-coordinate. So, x-coordinate isn't changing at all, that means. Let me continue. Yeah, I guess it's more the x-coordinate. The x-coordinate is changing at the first one. Second one, no. Throughout this course, we'll talk about 3 ways of thinking about derivatives. The first is graphical, as we can see by x function of x. We can see by this weird graph. What is the visual interpretation of the expression? Function of x minus function of a divided by x minus a in terms of the graph of f. the length of the the slope of the straight line connecting a function A and function X. What is the visual? In terms of graph F, the graph of F, length of the curve. I feel like it would be slope, most likely, when arguing. Yeah, slope. The line connecting A, function A, and X, function X, is called the segment line. As we can see in the diagram, the numerator at function X minus function A is the vertical exchange in the line from X to A, and the denominator X minus A is the horizontal exchange. The slope of the segment line is function X minus function A divided by X minus A. So, function of X minus function of A divided by X minus A is the slope of the segment line connecting A, function of A, and X, function of X. Can you visualize what happens when we take a limit as X to A? As X to as X to A, the segment lines approach what's called a tangent line to the curve of A, the line that only touches the curve near A once. Since this limit is the derivative, we say this. Graphically, the derivative of a function at A is the slope of the tangent line to the function's graph A. This should make sense in terms of the derivative being a rate of change. The steeper the tangent line, the steeper the curve, and the more f changes per change in x. That makes sense. Order from smallest to largest, the numbers FA, FB, and FC. The easiest look. In the slope of the segment line connecting A equals F, can you visualize what happens when we take a limit as X to A? Oh, look at this, how it affects the line. See? Look at it as it skips the curve. You see how it skips the curve? It's really interesting. And then this, here's a graph of a function f, smallest to largest. So would it just be height then, arguably? So we go C is the greatest. So CBA. CAB. Why is that? Oh, the exchange. Yeah, I see. Since the derivative of the slope of the tangent line, we have to compare the slopes of the three tangent lines. As we see, the slope of the tangent at A is smaller than the slope at B, but the slope at C is smaller than both of these. See, look at the graph. That makes sense. Okay, here's an interesting example. Looks like a triangle. Use the idea that the derivative is a slope of a tangent line. What do you think the derivative is at A? Wouldn't it just arguably be 0? I guess that would make a little more sense. It would either be 0 or just like nothing. We see that there's a problem trying to place a tangent line right at AFA. There are so many possible lines that only touch a graph at one point. The difficulty in describing a single tangent line is related to a big problem when we look at the limit itself. As we see here, when x is to the right of a, change in f, which is function x minus function a, is negative. So from looking at those x, we expect a negative value for this limit. When x is to the left of a, change in f is positive. Therefore, we have a situation where the limits as we approach from the left and from the right are different. As we saw earlier, that means the limit does not exist. So the derivative, which is defined as this limit, does not exist. We recall that the derivative is a limit of change in an output over change in input. That is a limit of change in y divided by change in x. This means when change in x is small, function prime a is close to change in y divided by change in x, or function a, or the function prime of a. Change in x is close to, or change in x is close to change in y. This leads to the input nudging view of the derivatives. Start at point A. Nudge the input a little bit. By how much did the output change? If the nudge was small, the answer will be very close to the function of the prime function of a times the amount you nudged x. In other words, the derivative is like a magnifying factor. Here, give me 1 second. So there should be a graph here. Maybe it'll load in a second. Let's just continue on. In other words, the derivative is like a magnifying factor. If the prime function of a equals 3, that means that when we move the input at a little bit, the output is moved by 3 times the amount. So that means the function of prime equals 3. That's when we move by the input a little bit. The output is... Let me take a picture of it. According to the input nudging view of derivatives, was a good approximation for the function of 10.1. So, would that be 100.4? Here, the change in x equals 0.1. Since the derivative at 10 is 4, the corresponding y is close to 0.4. We get this change in y to the function value at 10 to get 100 plus 0.4. That makes some sense. Yeah, it would be nice if we had a graph here. Yeah, there should be a graph here. I have no idea why it's not loading. Assume that the derivatives of the function of x equals sine x at x equals 0 is 1. We will look at the derivatives of trig functions soon. Using the input nudging view of derivatives, what's a good approximation for sine 0.2? So 1, would it just be that? 0.2 still. The derivative of 0 is 1, so a small change in x, we expect to see the same change in y. We're looking at a change of 0.2, and we're starting at sine 0 equals 0, so approximation is just 0.2. The actual value is 0.1987, continuing. Let's tie together the input nudging view with a graphical view of derivatives. Here's a picture of a graph of f while its tangent line at a. Let the change in x be the difference between x and a. And the last two questions, we've seen that f prime a, function of a plus the prime function of a times the change in x can be a good approximation to function of x. But how good is this approximation? Exactly how far apart are they? True or false? The absolute value between function of a plus prime function of a times change in x and function of x is exactly equal to the distance between points P and Q. Well, they do meet at relative parts. I'm going to say true. Correct. Clearly, the height of Q is function x. Remember that f prime a is the slope of the tangent line. So f prime a times exchange in x is the vertical exchange in the tangent line as we move from a to x, which we call change in v in this picture. Don't get confused by notation. Usually we will use change in y and change in x and note rise over run changes in a line, but in this lesson we've been using change in y for the change in the function value, which is very different. So we're calling the rise in the tangent line change in v. So the function of a plus the function prime of a times the change in x is the height of p, and the statement is true. To summarize, the derivative of a function at a point a is defined by the limit. The limit is x is a. The function of x minus the function of a divided by x minus a. We think of this as the rate of change of f at the point a. We will empathize 3 views of derivatives. Number 1, graphical view. The derivative is the slope of the tangent line to the graph of the function at a. Number 2, input nudging view. The derivative tells us when x is nudged a little by what factor of that changes the outputs of f will be changed. Number 3, symbolic view. We didn't talk about this one, but this is calculus, so we should be calculating things. In later lessons, we will learn how to take derivatives of functions given by formulas, polynomial, trig functions, and more. And then we can finish the lesson. That was a good lesson. Well, I wanted to say thank you for watching this video if you did watch the whole video. I know most people probably didn't watch the end, but I appreciate you did. And this was a good math marathon. It was tiring, but I did it all at once, so I would call it a good success. Thank you for watching.